All right, so let's just look at the 1D forces, and then we'll see about, we'll begin to add forces. So just the very basic one. Let's say I have an object, I have a force equal to 10 newtons, and let's say that it has a mass of 2 kilograms. What is its acceleration? Well, to do that, we say that the sum of the forces equals mass times acceleration. That's Newton's second law, and that'll always be our approach. In fact, here what we've done so far is just like the approach we have on the 2D problems. I've labeled my vectors. I didn't say it, but it's implied there that I use my coordinate system. I have that 10 Newton force acting on a 2 kilogram object, and so I have 10 newtons equals 2 kilograms times the acceleration, so A is equal to 5 meters per second squared. So my acceleration is in that direction. And then if I have multiple forces, say I have a 10 Newton force here and a 5 Newton force here, then the sum of the forces, well, it gets a little more complicated, right? I have now 10 minus 5 are a 5 Newton net force. So the total force on this object is not 10, but it's going to be 5. It's the difference in those two, because the 5 Newton force is to the left. That's why I subtract. And then if I want to know the acceleration, say that's equal to mass times acceleration. If the mass is the same, then that would be 5 divided by 2, or 2.5 meters per second squared. So that's sort of the next step, is that I begin to add forces. Then let's look at, we did these elevator problems. Let's imagine that I have an object that has two forces on it. Let's say an object that has a force, I don't know, 10 newtons. Well, we're doing exactly the same as what we had before. 5 newtons in that direction, then what is the acceleration on this? It's going to be exactly the same as the previous problem, right? Because here, the sum of the forces is 10 minus 5. If my mass is still 2 kilograms, then it'll still be 2.5 meters per second squared. So if we put that in the context of, say, the elevator, which is a problem that we did a couple of, where I have an object here, and let's say that it's accelerating upward at 2.5 meters per second squared, and it has a mass of 2 kilograms, or excuse me, not 2 kilograms, actually here it would have a, let's just say it has a mass of 2 kilograms, then what is the tension in the rope? Well, we want to first draw our forces. I have the tension in the rope there, and then I also have the weight. In this case, the weight will be 2 kilograms times 10, or 20 newtons. Who with me on that? It's m times g. So here, my mass is 2 kilograms. And that describes the amount of matter that's in the object. But the weight of the object is the mass times the acceleration. This is an actual force. So these are related to mass and the force, but they're different too. Always look and see, do I have a mass or do I have a weight? And you need to be careful, read the problem. If you have mass, which is usually the case, then you'll need to multiply by 10 to get the weight, where 10 is the acceleration due to gravity. Just be careful as you're reading through problems, because sometimes I give the weight and sometimes I give the mass. Just be careful with that. So now if I want to know the tension, I do the sum of the forces equals mass times acceleration. And then the sum of the forces is going to be Ft minus Fw equals ma. Now what do I know here? Well, I'm looking for Ft. So I say Ft equals Fw plus ma. That's going to be 20 newtons. That's Fw plus 2 times 2.5. Can I squeeze it in there? Yeah. That's my acceleration, which I got from right here. So that gives me 25 newtons. So the tension in this rope right here is going to be equal to 25 newtons. Notice that's more than the weight because it's accelerating upward. But what if it were accelerating downward at 2.5 meters per second squared? So instead of saying it's going up, let's say that it's going down. And that means that the acceleration now is going to be negative 2.5 meters per second squared. You work it exactly the same way, but you just put in a negative for the 2.5. Okay, so that would make it right here a negative right there. So instead of being 20 plus 5, it would be 20 minus 5, or 15 newtons. So if the elevator is accelerating downward, the tension in the rope is less than the weight. But notice we've been doing the same thing all along here, that every time all we're doing is we're giving our coordinate system and labeling the forces, giving them all on the x and y axes, and so far that's all that we've had. And then doing the sum of the forces equals mass times acceleration. So at its core, I understand that it's not easy. Like, it's difficult, but those are really the only steps that we're doing. And it's how you apply them where you get in the weeds. We'll come back in a bit and we'll look at some test questions. Let's go ahead and do it now, actually. Let's look at some old exams. Do you have any printed out? No?
I left them all at home.
Okay. Well, I'll just pull up some. What's in that? Is that 16 or 15?
15.
Okay. Well, I want to do 16. I don't think we've looked at this yet. Exam 2, fall 16. Okay, so let's look at 21. So 21 is a 1D problem. I'm going to draw my coordinate system over here. I have a force that's equal to the thrust over in this direction. Actually, it's equal to 4 times the thrust. I know that because there are 4 vectors here that all have an equal vector of t. And actually, I want to know what is the thrust of an individual rocket. But there are 4 of the rockets. So I have 4t right there. And then I also am told that the force of friction is 420 newtons. I know that friction always opposes the motion. I'm told that the acceleration is 25 meters per second squared. So A is equal to 25 meters per second squared. And then I'm also told that the mass is 1,200 kilograms. So, I say sum of the forces equals ma. I've labeled all my forces. I've put them on a coordinate system. I've written down what I know, the mass and the acceleration. And I say the sum of the forces is going to be 4t minus 420. That's equal to the mass, which is 1,200, times the acceleration, which is 25. And then I solve this for t. So that's going to be 1,200 times 25. It's 30,000. Plus 420 divided by 4. And I get, oh, that's not right. Uh, 7,600. So I get A is 7,600. All right, that's a basic sort of 1D problem. Let's look at the one about the woman who weighs 700 newtons. I think we did one similar to this in class. First of all, you know, her normal weight, but she's just sitting, not accelerating, is 700 newtons. But then she gets into an elevator, and it's now 800 newtons. What's happening? Is she going down or up in that elevator? She's going up, right? She feels there. You go in that elevator and you start going, it's like it pulls down on you. So she has 100 extra newtons that are reading on the scale. Now, if I think about this in my elevator, what's happening is that the normal force is your apparent weight. When you step on a scale, it's not your weight that it's measuring the normal force. And so this person is here. She has two forces acting on her, force weight and her normal force. And I know that her normal force is equal to 800 newtons. But her weight is 700 newtons. By the way, I know that Fw equals m times g, and so if her weight is 700 newtons, that means that her mass is 70 kilograms. So we'll need to know that her mass is equal to 70 kilograms when we're applying Newton's second law. Sometimes you might have to work backwards, and this is one of those cases where I don't give her mass, instead I give her weight. Be careful, you know, look at the words, think about the units. You would know that it's a weight because it says she weighs, and then also the unit here is newtons, not kilograms. But be very careful with that. Then I apply Newton's second law. Sum of the forces equals ma. 800 minus 700 equals 70 times the acceleration. So the acceleration is 100 newtons over 70 kilograms. That's going to be 1.4 upwards. I know that it's up because she feels heavier than when she is just normal. If it was down, what would it be? Let's see, if it was down, well, if it was 1 meters per second downward, what would her apparent weight be? Going up, it's 800 newtons. If the elevator is going up, she feels an extra 100 newtons heavier. What if she's going down at 1.4 meters per second squared? What do you think it's going to be?
100 less.
100 less, right. She wouldn't feel 700 newtons, she'd feel 600 newtons. That's right. Okay? You'll see similar questions to these. They'll be similar. This is a problem that has to do with kinematics, and you'll likely see something like this. It won't be a terribly difficult kinematics problem, but it'll be wrapped up with our Newton's law. So here, it has a force equal to 10 newtons. The mass is 2 kilograms. So I know from that my acceleration, which is F over m, is going to be 5 meters per second squared. And I want to know how far, that is, what does x equal after t equal to 4 seconds. So I say x is equal to v naught t plus 1/2 at squared. It's initially at rest, so v naught equals 0. That whole term goes away. So this is equal to 1/2 of the acceleration, it's 5 meters per second squared, times t squared, 4 seconds. 16, 8 times 5 is 40 meters. You'll probably see a problem like that. I think there's one. Okay. Okay, so once we get to these are where they get more difficult. Like 23 is a good example of something that you'll see on the test tomorrow. You'll definitely see, you'll see several 2D problems, either on an inclined plane, or like we did today with the guy with the rope that was pulling up on, or like the ones where we had the 2 ropes coming down, though you won't see any that are asymmetrical. So if you see one of those, it'll be like the one we did in class. If you want, we can do one a little later. Well, let's do this one right now, 23. The process is still the same. You're going to draw your coordinate system, label your forces. The only complication now is that you're going to have to resolve your vectors into the x and y components. So let's go ahead and draw the coordinate system. We'll always draw it like that. Now let's label our vectors. I have my tension, and I have my weight. I need to figure out, does this have any friction on it? If it did have friction, the frictional force would act down the inclined plane because it's moving up the inclined plane, always opposite the motion. But it says that it's a smooth incline. That means no friction. That's good. That makes it a lot easier. I know the angle here is 30 degrees. It says it here too. And I want to know what is the tension in the rope. So, my next step, I want to resolve those vectors into their x and y components. Here I have Ft. This is going to be Fw sine of 60. And then this is Fw cosine of 60. And then this is Fn. My normal force is right here. So you should get to some figure that looks something like this. And it's going to be different every time because it depends. Do you have friction? Where's the force acting? It's going to be a little bit different each time. So don't try to memorize what that figure looks like, but instead think about how do I take what I have here, these vectors, and draw them here with everything rightfully resolved and everything on the right axis. Sometimes that can be difficult, but it'll come with practice. Now we apply Newton's second law. In this case, I don't need to do anything with the normal force. The reason I don't have to do anything with the sum of the forces equals y, I don't have to deal with that, is because basically there's no friction. And so I don't need to know what is the frictional force. I don't need to know what is the normal force. But I could certainly find it. Like if I asked you what is the normal force, I would say the sum of the forces in the y, that's Fn minus Fw sine 60, that's equal to 0. And then I could solve for Fn. You with me on this? All right. What I really want to know is Ft. And I see that Ft right here. It's wrapped up in my x forces. So I do the sum of the forces in the x direction. It's Fw cosine 60 minus Ft. That's equal to the mass times the acceleration. Okay. You have to be careful with this problem because notice that your acceleration is up the inclined plane. So what is the direction? Is it positive or negative for the acceleration?
Negative.
It's going to be negative. Very good. But by looking at this, you might think, oh, it's going up the inclined plane, so the acceleration is positive. But the way that we've drawn our coordinate system, this is the negative x direction. So when I come down here to the acceleration, where was it? Right here, I need to put in a negative number. That is going to be actually negative 1 meter per second squared. I don't put that there, I just put the magnitude there, but the arrow is pointed in the negative direction. Okay, so I know Ft then is going to be equal to Fw cosine 60 plus Ma. What I did there is I added Ft, minus, wait, hold on, minus Ma. That's equal to Ft. So I bring the Ft to one side, and then I take the Ma over to the other side. I solve this for Ft. I have to add Ft to both sides and then subtract Ma from both sides. So I get the tension is equal to the weight. This is 2 kilograms, so it's 20 newtons. Cosine of 60 minus 2 kilograms times the acceleration. Remember, we have to be careful. This is minus 1 meter per second squared. So these will both go to positive. I'll get rid of those negatives. So, about 18 or so, I think. Oh no, 10. Oh, it's 12. Yeah, 12 newtons. We can sit here and do these all day long, but until you actually practice them on your own, you're going to have to really see that. But that's the process, that you label the forces, put them on a coordinate system, you resolve the vectors, and then you apply Newton's second law. When you do that, you'll get a couple formulae. You can get the sum of the forces in the y which we didn't need in this case, but if we needed to find the normal force, we could have. And then you do the sum of the forces in the x, which is what we did here.
So if it doesn't say like a smooth sloping problem, you should assume that they have friction?
Yeah, if there's friction, I will tell you something. Either I'll ask you for the coefficient or the frictional force, or I'll tell you what that information is. If there's no friction, I'll tell you it's smooth. If there's no mention of friction, then you assume that there's no friction. Okay? I'm pretty sure that I didn't... If there's no friction, I'm certain that I put smooth. Okay? But if there's no mention of friction, you assume that it's smooth. All right. Okay. So that's probably the hardest problem. These inclined planes are kind of difficult because you saw, even though there's only 3 or 4 steps, that there's lots of thought that goes into each step. And then they're solving the equations, and sometimes, like me too, you just sort of get lost in all the F's and the A's and, just sort of get all mixed up. But that comes with practice. As you practice more and more, you'll get better at it. Look, here's another one. This is another 2D problem.
Yeah, I think I got, because we did one like that in class, and I'm pretty sure I got confused on that.
We did one that was quite a bit simpler than this. This one is more difficult than the one that we did in class. The reason is that the one we did in class didn't have friction. And so that turned out to be not a terribly difficult problem. But this one does have friction. And so it changes the way that you work it, or it gives you some extra steps. So let's draw our forces. Actually, I'll just draw my forces over here. I have my normal force. This is our free body diagram. I have my kinetic friction, and I have my weight. And then I've already drawn this force. So those are the only 4 forces that I have. I always have weight. Because I have a surface, I have the normal force because it's pushing against the surface. And because I tell you about the friction, that's how I know it has a frictional force. So let's write these forces onto our coordinate system. This is Fn, Fk, Fw. And then I need to resolve this other force into its components. F cosine of 30, F sine of 30. Okay? I know that F is equal to 50, so I can go ahead and put in these values. This is going to equal to 25 newtons. This is 50 sine of 30. What's 50 cosine of 30? That's 43 newtons. I can also go ahead and put in my weight. It's 4 kilograms, so that's 40 newtons. I'm looking for the acceleration. I know that it's going to be accelerating along the floor. It's being pulled across the floor. And because it has friction, I know that it's moving in the x direction. And so I know that to find that, I'm going to be using this formula. Sum of the forces equals max. That's going to be 43 minus Fk. That's equal to the mass. Oh, I know the mass. It's 4 kilograms times Ax. So I could find the acceleration if only I knew the kinetic friction. But I don't know it right off. It's not given to me. But I do know that the kinetic friction is equal to mu k times the normal force. So if I can find the normal force, I can find the kinetic friction. And that's where the y motion comes in. Often if you have friction involved, you're going to need to find the normal force as an intermediate step, because that frictional force is related to the normal force. So to find my normal force, I say the sum of the forces in the y direction, these are always going to be equal to 0. That's going to be 25 plus Fn minus 40 equals to 0. So Fn equals to 40 minus 25, or 15 newtons. That's how I find my normal force. Notice that the normal force here is not equal to the weight. It's not equal to the weight because I'm pulling up on the object, and that makes the normal force less. It's like if you're, I like to put my little girl, like stand on the scale, and I'll push down on her so that, she's only like 50 pounds or whatever. But if you push down, it makes her look a lot heavier. Or if I pull up on her, she looks a lot less. She gets a kick out of weighing more or whatever. Anyway, so Fn is equal to 15 newtons. Now that I know this, I can come back and find my kinetic friction. So let's do that. Fk now is equal to mu k, which was 0.5, times 50 newtons. So that's 20, or not 50, times 15 newtons. So that's equal to 7.5 newtons. Whew, now that I have this, I can go take this, put it right here, and I'm almost home free. 43 minus 7.5 divided by 4, that will be equal to AX. I get 8.9, or 9 meters per second squared. All right, so B is the right answer. Again, one of the more difficult problems, and probably if you had this problem, it would be probably the most difficult that you would have. But it's similar in process to the 2D problems on the inclined plane. So it follows the same procedure. Label all my vectors, put them on a coordinate system, and then the hard part comes, you're writing out the equations and trying to solve them. If you have friction, you're almost always going to write 3 equations. Some of the forces in the x, some of the forces in the y, and then this whole thing with the friction, Fk equals mu Fn. There aren't that many equations. I know that we're sort of throwing around a lot, but really you have F equals ma. Little f, sorry, script f, is equal to mu times the normal force. Right, that's for both kinetic and static friction. And we have our kinematics, V equals V naught plus AT, X equals V naught T plus 1/2 AT squared. I think that's it. Is that it? And we have our trig functions. Okay, good. That's really it. I know that it seems like we have a lot of math, and we do, because the vector math gets complicated. But there aren't that many equations. So if you have these down, I mean, I think that you probably do. You probably know these pretty well by now. And then these are they're fairly simple. I think we know these. That's why you don't have an equation sheet yet. Okay, let's just sort of scroll down and see. Any questions though about this before we move on?
So the positive y and the negative y, they both equal the same. So is that going to be how it is in every problem?
If you're not moving in the y direction, then yes. Okay. So if it's sitting on a surface, the sum of the forces in the y direction will be equal to 0. But notice, on the previous problem that we worked, that wasn't true. Like in this problem right here, it was not equal to 0. That they weren't equal, rather. Ft was not equal to Fw. See, Ft was 15, Fw was 20. They're not equal if it's moving up and down. But when your object's sitting on a surface, an inclined plane or on a horizontal surface, then yes, they're equal. The forces in the y direction add up equals 0. Okay, let's see what else we got on that test. That's sort of the gist of those questions. You'll want to also know how to write these equations, but this is a precursor to being able to solve them numerically. Well, let's just look at these. We looked at one earlier. Fn minus Fw sine 30 equals 0. That seems okay to me, because I know that my normal force is in this direction, in the y direction, and Fw sine 30, well, let's just draw them. if you're uncertain about these, just label all the equations. And then you can compare them to what you see. This is Fn. This is going to be, this is my weight right here, Fw, and this is 30 degrees. So I have Fw sine 30, Fw cosine 30, notice in the negative x direction. And then I also have F. And I also know that my acceleration is in this direction. It's in the, actually I'm just going to label it as a positive acceleration in the x direction. That's what that arrow above the block is saying, that it's going up the inclined plane. So Fn minus Fw sine 30, what that's saying is that this force and this force are equal to one another, which is true. So that's okay. Oh, I do have kinetic friction. Okay, yeah, so my kinetic friction is going to be in this direction. The reason it's in that direction is because the block is accelerating to the right, so Fk is to the left. Always opposite the motion. So I have F minus Fk minus Fw cosine 30 equals max. That looks okay to me. F minus Fk minus Fw cosine 30 equals mass times acceleration. So that is okay. So this last one, oh, by the way, I know that 1 and 2 are fine. So that gets rid of this one, and it gets rid of that one. It's either A, B, or D. Oh, it gets rid of B as well. It's either A or D. So I need to check 3. Is 3 right? F minus Fw cosine 60 plus Fk. Things are going wrong here because, well, if this is cosine 60, this should say cosine 30, right? So this is actually a y component of the weight. Yeah, that's not right. So 3 is not correct because my angle is wrong there. So this one's not right. That means that A is the right answer. Every test that I've ever given has at least one of these questions. I would go back. It helps you to be able to write the equations. You have to be able to write the equations to actually solve them numerically. So go back and practice those. Now what else we got here? These are, some of our conceptual questions. I would go over the concept tests that are posted on Moodle. Go through and sort of quiz yourself on them. The questions that you see will be similar to those. All right? What else do you want to look at? There is no Newton's universal law of gravitation. So that G N M over R squared, page 81 and 82, you don't even see that at all. I meant to put it on there, I just forgot. So it sometimes falls off the exam. So no universal law of gravitation.
It's pretty much like what we did is like pretty much chapter 4. Like what we
That's the bulk of chapter 4, yeah. It's applying Newton's laws. And we didn't go over some of the conceptual stuff about, what are the laws, the law of inertia, law of acceleration, law of action-reaction, the relationship between force and mass. So a bigger object mass will need a greater force to accelerate at the same rate. That's all exploring that F equals ma relationship between those variables. Alrighty?
I think I could get the hang of it. Since now that I don't know. Like it's easier now than it is in class, but it's the same exact thing.
It is the same, right? It is the same one, really. It's okay. Every time you see it and every time you practice it, it'll get a little bit easier.
That's how like the last test. I think I stayed up till like 1 in the morning, but like I was finally starting to get it, so I didn't want to go to sleep.
Right, you did well. Is that all for here? I'm going to stop this.